Hello everyone, welcome back. As we already discussed in our previous video about moment of inertia, now let us try to derive the expressions for moment of inertia of regular figures. So one of them is thin uniform rod. So for the thin uniform rod, we can calculate moment of inertia about different axes of rotations, out of which now in our first video, we are going to learn or derive moment of inertia of a thin uniform rod about an axis passing through the center of mass and perpendicular to its length. So you can see in the diagram over here. So this is a thin uniform rod, and say this thin uniform rod has a length L. Okay, how much I am considering? Length L. Clear? And say this thin uniform rod also has a mass M. Also has mass M. Total mass be M. So therefore, as already in our previous video at the last, we have seen the formula for calculating the moment of inertia for a continuous mass distributions like this. So that is given by I is equals to integral r square dm. Right. So what is dm, sir, here? So the dm is a small mass element which we are going to consider at any point or at any distance on this thin uniform rod and integrating that one for the given limits over this thin uniform rod, and we will be calculating the moment of inertia. So for such things, I will be calculating or I will be considering a small mass. You can see over here. So small partition. See this one. So I am just considering this part. You can say I am shading it. Say this is dm. I am considering this mass as dm, and say this smallest mass is situated at a distance of x from the origin. Let me suppose this center of mass be origin. So now what are the limits I can assume for this one to calculate the integration? Say this is minus L by 2, because center of mass for a thin uniform rod lies at the center, so it divides the length into two equal halves. So therefore minus L by 2 plus L by 2 are my integration limits, and this is your x, so that is the distance. So here r square, where r is the distance between the small mass element from axis of rotation. So in the diagram we can see for the small mass element, the distance of this one from the axis of rotation is x. So therefore here in the place of r we can write x. So now what about this dm? How to define this dm? So as we already know about few basics of this one, we can say this is linear distribution of mass. Here this one we can consider about as linear distribution of mass. So therefore for the linear distribution of mass, what I can say directly, lambda is equal to mass per unit length. So from this I can say directly m is equals to lambda into L. So therefore from here I can easily or simply write it as dm for a mass of a smaller mass element is equal to lambda times d. What is this length along x-axis we considered? So I would like to consider this one as dx. So thus replacing all these terms in your integration, we will get the moment of inertia as follows. So I is equals to limits minus L by 2 to plus L by 2, r square is x square, and dm is written as lambda dx. So therefore directly let me substitute this one. I is equals to lambda is anyway constant, comes outside, integral minus L by 2 to plus L by 2 x square dx. So integral x square dx is similar to that of integral x to the power n dx. So integral x to the power n dx is given by x to the power n plus 1 by n plus 1. So let me write this one only. So lambda into, this will be x to the power n plus 1, that is 3, by x to the power, sorry, n plus 1, that is again 3, and this is varying from minus L by 2 to plus L by 2. So substituting the upper and lower limits will become lambda into, this will be 1 by 3 also. I would like to take it outside, so therefore I can take lambda by 3 as this one, and this is x cube. So L by 2 whole cube will be L cube by 8 minus L by 2 whole cube will be minus L cube by 8. So on simplifying this one, I will get it as directly this one, moment of inertia I is equals lambda by 3 into L cube by 4. L cube by 4. So where lambda, now let me substitute lambda also. What is lambda given? Mass per unit length. So that is 3L into L cube by 4. So cancelling 1L will result you moment of inertia about center of mass passing perpendicular to the thin rod is ml square by 12. That's it. So this is your moment of inertia expression for moment of inertia for a thin uniform rod about an axis passing through center of mass and perpendicular to the thin uniform rod. And from this we can even find out a radius of gyration also. So radius of gyration is given by directly denoted by k, radius of gyration, and is given as I is equals to mk square. I is equals to mk square, and for this problem it will be mk square is equals to ml square by 12. On simplifying which I get k is equals to L by root 12. Sir, what is this radius of gyration, sir? So radius of gyration is simply nothing but the distance from the axis of rotation of the center of mass through which this moment of inertia of the total mass is said to be concentrated, and the distance between that point to the axis of rotation we call it as radius of gyration. In the figure, if you want to calculate the radius of gyration for this center of mass and for this center of mass on either halves, you need to calculate, and from the axis of rotation we'll be calculating the distance, and that will be your L by root 12 as your radius of gyration. So hope you all understood. So in our next video we will take the help of this video only, and we will be calculating the moment of inertia about another axis for the same thin uniform rod, and thus we can show you that as depending upon the axis of rotation for every rigid body, its moment of inertia also changes. Thank you. Have a great day.